this video, you have a charge capital Q that is fixed and a second charge little q of mass m that is initially moving towards the charge capital Q with speed v. In the beginning, it's at a distance 2L, and a goal is to find the speed of this charge when it's at point P, which is a distance L from the charge capital Q. Now, the two charges are positive, so physically, you should ask yourself, what do we expect? Do we expect the speed to increase or do we expect it to decrease? Okay, so let's address this in your mind. Just come up with an answer, and then as we move on, we'll try to figure out what exactly happens and whether it makes sense, whether what happens. Okay, the question is, we want to find the speed, so we have to ask what concept are we going to use? Okay, at this point, you should be able to figure out why we cannot use forces. All right, and again, the reason is that as this charge moves towards capital Q, the force itself is changing because its position is changing, the force is changing, which would require us to use calculus. However, because of the fact that all these forces are conservative, we can use mechanical energy ideas. So we could use MEI equal to MEF to figure this out. Now, when the charge is at a distance 2L, okay, it's moving with speed v, and its distance is 2L. So we know the mechanical energy in the beginning is going to be 1/2 mv square plus the potential energy term, which is capital KEQQ over 2L. Okay. Now, when it is at P, the kinetic energy term will be, say, 1/2 mvf square and then plus KEQQ all over L. Okay. Now we can solve this by moving terms to the other side. So we get 1/2 mvf square is equal to 1/2 mv square plus KEQQ over 2L minus KEQQ all over L. Now when you do this, we are left with minus KEQQ over 2L. Okay, when you subtract half minus 1, you end up with a negative half. And I have 1/2 mv square on this side. So this tells me that Vf square is equal to, so if we can just do some, divide both sides by, multiply both sides by 2 and then divide by m, we're left with V square on this side minus KEQQ over 2L times m. Okay, and so this would end up giving us the speed Vf as square root of V square minus KEQQ over, oh, actually no, there's no 2, over L times m. Now going back to the question I asked earlier, what do you expect the speed, what do you expect to happen to the speed? Should it increase or should it decrease? Now clearly you see in this problem that the speed has gone down. Now, does it make sense? Ask yourself, okay? As the particle gets closer and closer to the big charge Q, the repulsive force is increasing, so it has to slow it down. Okay, so the answer physically does make sense. Now, another question that we could ask is, at what distance will it stop? Okay, so as it comes closer, since this force is becoming larger and larger and larger, at some distance we expect the particle to stop moving. Okay, so let's calculate that distance now. In order to do that, we'll go back to our original equation for energy conservation, and we'll rewrite this as 1/2 mvf square plus KEQQ over 2L, and then this would be equal to 0 for the kinetic energy plus 1/2, not 1/2, plus KEQQ over some D. Okay, now we can just move some things around here and then end up solving for D. So we could do D over KEQQ would be equal to 1 divided by, we have all this 1/2 mvf square. Oh no, sorry, this should have been mv square. mv square plus KEQQ over 2L. And so D would be KEQ over 1/2 mv square plus KEQQ over 2L. Okay, now obviously in this problem I started my initial distance at 2L. If I had started it at some D, then just replace the 2L with D or some other L, some other quantity, and then you can use this to find the distance at which the object would stop moving. All right, hopefully you understand the parts for this, and in the next problem we'll take a look at some other ideas.